Awesome. So we're Group 4, and I'm Edwards, and I'm accompanied by my colleagues Aminul and Tobias, and we're just going to talk through what we've been working on, basically. Our project title is Digital Twins for Underground Infrastructure Inspection. And I wanted to start off this presentation by just sort of explaining what that means, because the first time I read that, I was like, I have no clue what that means. So basically, we're making a robot to map pipes from the inside out, and I'll talk about it a bit more in a bit, but this is the sort of thing that we're talking about. And one of the reasons that this is so important is that pipe mapping is a big industry. In the US alone, 2 to 3% of all natural gas produced per year is lost due to leaks and poor fitting in pipes. And that basically equates to about $2 billion in lost revenue. And it's not just natural gas, there's all sorts of things that are transmitted in pipes or transported in pipes. Water, oil, and then other things as well to consider like sewage. So you've got monetary benefit of ensuring your pipes don't leak and also environmental benefit of ensuring they don't leak. Now the main way pipes are currently tested is hydrostatic testing, which is where you seal your pipe, you pressurize it, and if it holds pressure, you're good. If it doesn't hold pressure, you dig up around it and you look for leaks. And as you can imagine, that's quite expensive, You have to dig up the area, close roads, and, it's quite a simple way of doing it, but there's a large cost involved in that. So over recent years, it's been sort of leading the way in sort of mapping pipes from the inside out and inspecting them from the inside out. And there's a company called PureTech, one of many, that make a product called the Smart Ball, which is similar to the design we've gone with. It's a ball that you roll through a pipe. It maps the inside of the pipe using a variety of sensors. That ball is extracted from the inside of the pipes, and then that data is taken away by PureTech. They analyze it, and 48 hours later, you get given dig sites as where you need to dig and perform your repairs. So you can tell from what I've said so far that mapping from the inside out seems to be the way forward. You've got to, you're already inside the pipe, you can check it quite easily rather than having to dig up around. But what we wanted to do is rather than have this 48-hour turnaround time, which in most other technology, you just wouldn't use the service if it took 48 hours. For example, like, if you sent an email and they're like, oh no, we're going to send it in 48 hours, mate. You'd be pretty annoyed, wouldn't you? I know it's not quite the same, but we wanted to relay the data live. So the idea is that the data would be transmitted out and you could visualize that data in 3D. And rather than just be told where to dig, we're starting with the basics of mapping the pipe and seeing what it looks like. So sort of overview of our project in this lovely diagram is we have two balls. We have a fixed ball and a rolling ball. This is one of the prototypes. And essentially the fixed ball acts as sort of a starting point. You have a GPS antenna attached to it, so we can get this location in the real world. From there, the rolling ball moves down the pipe, and as you can imagine, you're not going to get GPS data underground. So we do have the antenna coming out, and this ball doesn't have GPS. But it does have UWB, ultra wideband, the technology that's used in the Apple AirTag. Relatively old technology, but just coming into the market, being used in sort of location tracking relatively recently. And we can get quite an accurate reading of how far away the ball is from the fixed ball, and thus we know where that is in the real world too. On that ball, we have a load of sensors. We have time of flight sensors, 9 DOF, 9 degrees of freedom, or a gyroscope in other words, and then some extras, humidity, temperature, pressure. And basically with the time of flight and the 9 degrees of freedom gyroscope, you can work out where the ball is in terms of what orientation it's in, and the sensors evenly spaced outwards give you distance readings of what the pipe looks like on the inside. That data is transmitted back via Bluetooth to the fixed ball, and then from the fixed ball out, Wi-Fi to AWS over an IoT protocol, MQTT. And then it's processed through a number of services in AWS and finally finishes up with a sort of live map image of the pipe. So going into the workload split, I myself are responsible for the enclosure, which we've been 3D printing and working on designing that to ensure that all the hardware can fit in. I'm then responsible for the majority of the hardware and the embedded systems, so everything other than the time of flight sensors, that's me. And then that Wi-Fi transmission, so getting the data from the stationary ball over MQTT to AWS. Aminul is responsible for the time of flight sensors in the ball, so getting distance measurements from them. And then the SLAM algorithm, which stands for Simultaneous Localization and Mapping Algorithm, which is basically where you take all that data, the UWB, the GPS, and all those distances, and convert it into a 3D point cloud. He's also responsible for the Bluetooth transmission of the data between the two balls. From there, Tobias takes all that data from AWS, visualizes it in 3D. It's going to start off as a web application that's in progress, and then hopefully, if time allows, that will then develop into an Android application. So going on to what I've done so far, I've spent a large amount of time working on the casing. Obviously, with what we're coming up with, it's going to have to be custom made. It's been quite tough to get it to work. It's essentially, it's got 4 different threaded parts. It screws together, and the idea is that then one of these would roll down the pipe and the other one would be the stationary ball. I think that's about version 9. I've printed about 5 million times, it feels like, just to get it to work with the different tolerances. It's been a bit of a pain, but it's there at the moment, so yeah. In terms of actual hardware, we've got GPS, UWB and MQTT, like I mentioned earlier. I've got them currently on breadboards working. I can get distances between the 2 setups. I can get MQT transmitted to AWS, and I've got GPS live data being received. Other things to consider is batteries. We're using LiPo because of the microcontrollers we're using. They've got inbuilt power management, so you can actually just plug and play with the LiPo batteries. And then also we've got some indicator LEDs, touch button. I've got them working as well on sort of prototyping the breadboard stage. The LEDs, basically all they do is they just provide some form of feedback. You know, a screen would consume too much power in this scenario, so just some LEDs and being able to press a button. And I'll come on to this a bit more, why we went down the route of the touch button and other things. But yeah, that's my progress so far. Going from there, obviously, I can't fit a breadboard in here. It's, it's too small. So we're going to do some custom PCBs. I'm currently working on designing them at the moment. They're in the works. They're not quite finished, but they'll house all the, connect all the different hardware together that we've currently got at a prototype. We're also going to implement wireless charging. So one of the reasons that we were going down the wireless charging route is a sort of initial aim when we started with this project of making the product waterproof. And I'll talk about that a little bit more on the next slide. But yeah, so I've got all the hardware to do the wireless charging. Similar to like if any of you have Oral-B toothbrushes, it's just, it sits on the dock and it'll charge up and it'll have, the LEDs will light up. So it's, and then from there, bill of materials, to get those last little bits of hardware in. Assembly, I'm probably going to print this again as well, so need to print that again. And then testing, we've got a cardboard pipe that we're going to simulate it in, so we're just going to simulate it in a dry environment, just as a proof of concept. So basically from there, I just want to emphasize that the product that we're designing is a prototype. As the product's developed, it's become apparent that there's a lot of considerations you need to think about when working in an active environment, such as, underground pipes. For example, if this was in a an active pipe, you'd have to consider one of the things is wireless signal propagation. So wireless signals don't tend to propagate very well underwater. Similar problem to you have with submarines. So it does throw a spanner in the works in some of the designs that in some of the ideas that we chose early on. UWB, Wi-Fi, Bluetooth. So we're just going to test this in a dry pipe as a proof of concept of the live mapping of the data aspect. Going on from there, like I talked about waterproofing. When we first chose this project, there was a big emphasis on the product being waterproof. And as the product's developed, there's been a number of things that lead into that. So I talked about on that earlier slide, there's the capacitive touch button. Obviously that's a sealed system and it detects the, behind the plastic. And then also we've got the wireless charging that leads itself into the waterproofing aspect. And then the whole product, I don't know if you can all see it from here, but basically screws together in 2 halves and we have a nice seal around the end. So the idea is that you'd have a friction fit and that would hopefully hold it together. Another consideration in that is it's 3D printed, it's layers of material, so it would have to be printed at enough infill to ensure it's waterproof. Now the astute among you will probably notice that I'm chatting a load about waterproofing, but there's 6 holes in the casing. So that's basically because as the project's developed, the time of flight sensors we've discovered are more accurate when they don't have anything over them. So you can calibrate them so they have glass over them, but it's kind of, as we're not going to be testing this in a live environment, we just decided to skip that for the moment. In conclusion, I feel that I could have reached where I'm at slightly earlier, but it's been pretty tough to get it to work. I've had a number of issues with AWS and getting with the MQTT, so the transmitting of data from the microcontroller out to AWS. I've had a number of issues with that's all the authentication within that and using certificates and things. But I'm pretty happy with the progress. I'm on track with my sort of part to finish up on time for the deadline. And just to re-emphasize, it is a prototype. A number of the issues that I've mentioned could be solved by implementing this on, I presume a lot of you have seen this before, it's a Sphero. It's a very similar concept to a hamster in a hamster wheel. And basically the idea would be that this project could then be extended, further, and that would be the hardware that we've come up with could then be implemented into a device like this, thus eliminating a lot of the problems that we've exhibited with sensors and things like that. Yeah, so that's my part. Thanks very much for listening, and I'll pass over to Aminul.
So in this project, I'm responsible for the development of the simultaneous localization and mapping algorithm. SLAM algorithm is basically allows you to map an environment and at the same time locate the position of the device that is mapping the environment. In our case, that device is the rolling ball, and the environment is the inside of the pipe. For the localization of the rolling ball, we are using the UWB data provided by Edward. So we'll know the position of the rolling ball respect to the fixed ball. And to map the inside of the pipe, I'll need to create a point cloud data. Point cloud data is basically made up of points, with each point having geometric coordinates x, y, and z. And when you have a collection of these points, you are able to represent any objects in 3D. In our case, the pipe. For mapping the inside of the pipe, I'm using 6 time-of-flight sensors. These sensors are able to measure distance, and to program these sensors, I'm using the feather sense board by Adafruit. This board has also a gyroscope integrated. I'll be using the gyroscope to know the direction at which each sensors are pointing. And then combining the readings from the sensors with UWB data, I'll be able to generate the coordinates of each point. I'm also responsible for the transmission of data between the balls. I'll be using Bluetooth low energy to transmit data between the rolling ball and the fixed ball instead of classic Bluetooth because Bluetooth low energy consumes less power respect classic Bluetooth. There's a problem with this is that Bluetooth low energy is not able to transmit a large amount of data respect to classic Bluetooth, but in our case we are not transmitting a lot of amount of data. So therefore it's ideal using Bluetooth low energy. This will increase the battery life of the balls. As a backup plan, in case this transmission of wireless data is not working, we also intend to include an SD card in the balls where the point cloud data will be stored. For now, I was able to test the Bluetooth connection with my phone. I was able to get readings from the sensors from one of the balls to my phone. The remaining works to complete the project are to complete the development of the SLAM algorithm, more specifically combining the sensor data from the time-of-flight sensor data that I'm receiving now with the UWB data and gyroscope to get the coordinates of each point and then create the point cloud data. I also need to finish the communication between the balls with connecting the 2 balls with via Bluetooth. While working in this project, at the beginning I had a few issues, one of which is I wasn't able to get all the readings from the time-of-flight sensors at the same time. This is because these sensors have a unique address which is the same for all of them. but you are able to change them on the software part. But this change is not permanent. Therefore, each time the device is turned on, you have to change the address so you can get the readings at the same time. Progression-wise, I think what I've done so far is a good amount of work, and if I continue to work as I did until now, I'll be able to finish the project. Now I'll pass you to Tobias.
Yeah. So for my section of this project, I will basically be taking the point cloud data generated by Aminul's algorithm and using this to generate a model that I will then display in augmented reality. And I will use many different tools to accomplish this. Two of the most basic tools that I will be using is WebXR and Three.js. WebXR is a web API that basically tells your web browser how it should interact with a VR headset or your smartphone to display 3D environments and experiences. While Three.js is an API that you use to model scenes and interactions in 3D environments. So you might ask, why did we decide to use augmented reality to display our data in this project? And that's because we want our model to be updating in real time. So while the ball is rolling through the pipe, you will be able to see the model in the real world expanding and, yeah, basically mapping it. And we want to be able to map it to the real world, so you will see the pipe where it is in augmented reality as well. So this is a basic overview of all the services I'm using and tools. So it basically goes like this. Every service is hosted on AWS, which is Amazon Web Services in the cloud. So the information is sent from the ball into the Amazon IoT core. From there it goes to DynamoDB, where it is stored, where it then sends it over to Amazon Sumerian. The IoT core basically connects IoT devices such as our microcontroller to different AWS services. It does this using a protocol known as MQTT. MQTT works by having a message broker and subscriber or multiple subscribers. In our case, the broker will be the IoT core service and the subscriber will be the DynamoDB service. So what is the DynamoDB service? It is sort of like an Amazon's database service, and we'll be using it to store our point cloud data. So it will receive the messages from the IoT core and then store them in a JSON format in a sort of table. And this database will be continuously updating, so it will be expanding for the duration of the ball's rotation down the pipe. And it will also, at the same time, send out point cloud data further to Sumerian, while also retrieving these messages. So, what is Amazon Sumerian? Amazon Sumerian is basically a service for creating 3D mixed reality applications, and you can think of it as sort of like a game engine, similar to Unity or Unreal Engine. The difference is that you don't have to download Amazon Sumerian, so it can easily be created and published within your browser. The only thing you need to consider is that your browser needs to be WebXR compatible. So since we are creating augmented reality experiences, the optimal way to view our scenes is on your phone. It's possible to view them on a laptop in Firefox or Chrome, but you will have to, for Firefox you need an add-on, and for Chrome I think it's possible to do it by default, but obviously the experience won't be as good as it would be on a phone. So Amazon Sumerian receives the data from Dynamo database and creates a 3D model based on this using the built-in tools of Sumerian in combination with Three.js. And it's basically two methods we have thought of for displaying the pipe. The first method is Sumerian receives the point cloud data and based on this creates a model that it expands through time. Or the second method is to have a pre-existing model of the pipe within Sumerian, and then as it receives point cloud data, it will add these points onto a pre-existing model of the pipe. So, some of the remaining work I have to do is to get IoT Core to send messages over to Dynamo. Dynamo needs to be able to retrieve these messages from the IoT Core and save them. There's also the question of, do we even need the Dynamo DB Core? We could maybe connect the IoT Core directly to Sumerian. But I prefer to have the Dynamo DB Core still in use, since the only other place the point cloud data will be stored is in the SD card within the ball. So you would have to dismantle the ball, get the SD card, plug it into your computer, import the data into Sumerian to then generate a model. So if the data is also stored in Dynamo, it would be better if you later want to view the data again. The last thing I have to do is get Sumerian to import the data from Dynamo and get it to display point cloud data within the scenes of Sumerian. In conclusion, some of the things I've learned and wished I did earlier within this process is I should have started on the AWS services earlier. In the beginning, my focus was very narrow, and I focused on specific tools like 3JS and WebXR a lot, and I wish I spent more time on something like AWS, because 3JS is basically just a modeling tool, and I was very focused on this, and it took a lot of time. Something else is we have thought about adding features to the ball, and one of these features is a phone app that I believe we will be able to complete. I've started looking at AR Core and Android Studio for creating apps